So what I want to do here is derive some recurrence relationships for Chebyshev polynomials, and the way that I'm going to start, like we normally do, is by looking at some ordinary trigonometric properties that we're familiar with. And there are two in particular that I'm going to look at, and those are cosine of A plus cosine of B. That's equal to 2 times cosine of A plus B over 2 multiplied by cosine of A minus B over 2. Boom. All right. And we have a similar one for sines. We have sine of A plus sine of B is equal to 2. And now it's sine of A plus B over 2 multiplied by cosine of A minus B over 2. Cosine of A minus B over 2. Okay, so we've got this. Now, what I want to do is just look at what happens for a specific choice of A and B. So what I want to do is pick A being equal to n plus 1 times theta, so some argument, and B being equal to n plus, or rather n minus 1 times theta. And let's just plug this in and see what happens. So we plug this in, what do we get? We're going to get, for the first one up top, we're going to get cosine of n plus 1 theta plus cosine of n minus 1 theta. This whole thing's equal to 2 times, well, what are we going to have here? Cosine of A plus B. Well, in that case, this 1's going to cancel out, and we'll have 2n, so this will just be cosine of n theta multiplied by, what's this right here? We're going to have cosine of n plus 1 minus n plus 1. So the n's cancel out, and now the 1's add. And this is just going to be cosine of theta. Okay, so this is already kind of neat, right? Because what this tells us is that if you have, say, cosine of 2n, right? Or cosine of, yeah, cosine of n plus 1, then you have now generated a recurrence relationship, which will get you another set of trig identities for higher values of n. And this isn't something that people normally think about, right? Because normally we just say, all right, yeah, you have cosine n, cosine n plus 1, great. And you don't often think about, developing recurrence relationships between those. But that's exactly what this is right here. It's a recurrence relationship between different cosines. So that's already kind of neat. But we can step it up even further. And really, what's the application to this case? We're looking at Chebyshev polynomials. So let's actually plug in some Chebyshev polynomials and see what happens. So this right here, and I guess I should remind everybody, our Chebyshev polynomials defined in this way: cosine of n theta, and we've got a whole bunch of n thetas hanging around. So if we use the change of variables x equals cosine theta, what happens? Well, this is going to become a Chebyshev polynomial t sub n plus 1 of x. This will become plus t sub n minus 1 of x. Whole thing equal to what? 2 times t sub n of x times cosine theta, that's also known as x. And so here we have a very simple recurrence relationship for Chebyshev polynomials, where if you know, say, t sub 0 and t sub 1, you can generate all the other ones from it. Okay, that's neat. Let's try and do the same thing now with this second property right here, with our sine. So if we use the same a and b as before, what we get is sine of n plus 1 theta plus sine of n minus 1 theta. This whole thing's going to be equal to 2 times sine of n theta times cosine theta. And I should probably remind everybody again, our Chebyshev polynomials of the second kind are defined like this. It's u sub n of cosine theta. It's equal to what? It's equal to sine of n plus 1 theta divided by sine theta. So what happens here? Well, we have a lot of sines of n, a lot of sine of n plus 1, n minus 1. But we're lacking the sine theta right here. So if we divide every term here by sine theta, divide everybody here by sine theta, now we have something that looks a lot like Chebyshev polynomials of the second kind. And we can plug those in, and what we get is that, well, this first term right here, this is going to just be un of x. The second term right here is going to be un minus 2 of x, right? Because n minus 1 becomes n minus 2. And this term right here is going to be what? This is u sub n minus 1, and this cosine theta here is also known as x. So here we go, we have another recurrence relationship, and we can shift all these indices up by 1. If we shift them up by 1, then what we see is that this recurrence relationship right here is actually exactly the same as our recurrence relationship for Chebyshev polynomials of the first kind. And so our two recurrence relationships for Chebyshev polynomials of the first and second kind are actually the exact same, which is pretty interesting. But it also raises the question: well, wait a minute. If these two recurrence relationships are the same, then why aren't our polynomials the same? And the reason for that is, of course, that our first two starting points, our sort of initial conditions for our recurrence relationship, are different in each case. So for our Chebyshev polynomials of the first kind, we have the initial conditions that t sub 0 is 1 and t sub 1 is x, whereas for our Chebyshev polynomials of the second kind, our initial conditions are that u sub 0 is equal to 1 and u sub 1 is equal to 2x. And so it's this difference right here with t1 and u1 which account for the difference in our Chebyshev polynomials as you go through this recurrence relationship. So yeah, we've derived a super cool recurrence relationship between our two Chebyshev polynomials, and now we see another parallel between our two Chebyshev polynomials.